The title of this lecture was CC3D HPC for neural network surrogates. We'll talk about neural network surrogates, but we'll probably not have time to do exercises on it. So we have 1 hour and a half to cover HPC, pure Python, deploying online, and neural network surrogates. And since the priority of this lecture is HPC, we'll go over on what it is. And given the limited time, we'll probably focus more on HPC. And if you're running out of time, we'll sacrifice neural network surrogates and deploying simulations online. But I'll make sure I at least talk about them. Okay? All right. So module 9.3, welcome back. My name is Pedro Cenci dal Castel. This is a lecture on pure Python, CompuCell3D for high performance computation. Thanks to our supporting institutions, NSF, IUB Biocomplexity Institute, OpenVT, Glimprint, and previous funding from NIH. Okay, so the learning objectives of this lecture are, first, give you instructions on how to generate a pure Python CompuCell3D simulation. So this is not not mandatory to run on clusters, but it does make easier to build scripts because you can run your CompuCell3D with just one line of command. Give you the steps to set up a CompuCell3D environment in a Slurm cluster, specifically Slurm, because it's the one I use. You may find other cluster systems out there. In this case, you have to learn about the specific cluster you're using. I'll also explain the workflow of a script that runs CompuCell3D simulations in a cluster. Like, for example, looping over parameters, creating files and folders, copying the simulation, and submitting jobs to the cluster. We'll discuss what is a neural network surrogate and what do we care about neural network surrogates. I'll also explain the workflow of a neural network surrogate. If we have time, I will show you how it looks like in actual code. Then I will show you an online deployed pure Python simulation. So this is something you can more easily do if your simulation is uh, pure Python. You can still use XML. So I have to correct these slides later. But with pure Python framework, it's easier to deploy your simulation because you write them in a Jupyter Notebook, and there are websites out there that support running Jupyter Notebooks online. Okay, so what is not the purpose of this lecture? So there are many things that you might be expecting and we will not do. So for example, we will not run a simulation on an HPC, on a cluster. We cannot provide you with access to a cluster, so it's very unlikely that we'll get everybody to replicate what I do here on the screen. So I will do a lot of demonstration and talking, and we'll have only a few exercises. We will also not run a script on an HPC, same reason, and we will not build a neural network surrogate. If we have time, we may train a neural network surrogate with a given dataset, but it's not feasible to build one from scratch within 30 minutes. We'll also not deploy a simulation online because that requires, for example, setting up your GitHub repository, a YML file, and having a workaround for lattice visualization because the website I use, which is Binder, is a headless environment. It does not support the built-in CompuCell3D visualization. We'll also not go over all the scripts line by line. We'll mainly go over the pure Python simulation line by line, but the others, like the scripts that I run in the cluster, will not go line by line because they are specific to the system and also specific to the purpose of your project. So I will explain the framework. The framework is more general, so the pseudocode rather than going over the code itself. So this is only for guidance. Um, for example, to run your simulation on a cluster and train neural network surrogates. Building these scripts is a tough job, so you need to be resilient, organized, and proactive. Ask us for help. Ask ChatGPT for help. Ask other AI assistants for help. And tune down your ego so that your chances of calling for help are higher instead of stalling on your project for months. Organization is really key here because often systems update and then you want to keep track of your scripts that have worked in the past and don't work anymore. Or sometimes you change your scripts and suddenly you lost valuable code that you had a few months ago. And maybe the best advice is to start small. So if you want to run 1,000 simulations on a cluster, start by running just one just one simulation and not even the simulation you are working with. Start with a minimal simulation, with a simulation that just has one cell, just has volume constraint. If that works, it means that the framework is in a good place. So before you go to thousands of runs, thousands of parameter sweeps, high dimensional parameter analysis, these kind of stuff, start small. Start with small number of replicates, small simulation. So don't run your simulation for thousands of steps. Run them for 2 steps and see how it works. Once you have your entire workspace set up, then you test it twice. It has to be at least twice because sometimes you are overwriting files, and if you test only once and it works, then you do a run for real, and suddenly you are overwriting files, or you are writing on top or appending to files, and you can create a big mess. So why do we use high performance computing for CompuCell3D? So, for example, with classical CompuCell3D running on your local machine, you can do parameter scans. So Jim showed that 2 days ago or yesterday. I think it was yesterday. You can do parameter scans. You can also do optimization scripts, but it is limited. For example, if you want to run 100 simulations simultaneously, probably using your local machine is not a good idea. For example, my machine here is pretty good. It runs some very heavy games here from Steam. You always see my Steam pop-ups on the corner. So it run good games, last generation, but it can only run about 5 simulations simultaneously. In a cluster, I can run typically 500 simulations simultaneously, which is a big leap because if I need really good statistics for my averages, for example, nowadays I'm working with virus spread, and this is an extremely stochastic system because whether one virus infects a cell or not has a very big impact on the outcome of the simulation. So I am doing 200 replicates of each parameter set. And doing that locally is simply not feasible. Also, running long simulations may interfere with your daily activities, and clusters typically allow 24 hours of processes. Rendering the lattice might be tricky in the cluster. It depends on the system. Um, Especially if you are doing pure Python simulation. If you are using normal CompuCell3D on a cluster, I don't know how to set that up, but it is possible people do that. Then it's easier to set up because player has built-in visualization tools. But even with classic CompuCell3D, you might find issues, and sometimes they update the cluster, and with a new update, you start to find issues. And this is not something that we can trivially solve. Oftentimes, you have to speak with the administration to solve the problem. So issues you may encounter when accessing cluster and installing CompuCell3D. Oftentimes you need to subscribe to a cluster or you need authorization from your institution. So for example, here in IU, I need authorization from the university to access Big Red 200 and Tatooine, which are the two clusters I use to run my simulations on. You have to obey protocols, access request, permissions to access certain folders inside the cluster and install software. So sometimes you have access to the cluster, but it doesn't allow you to install software. In this case, you may have to ask permission from the administration. Getting information about what you can and cannot do as a user of your specific cluster often requires emailing your cluster administration and reading documentation they provide online. Installing CompuCell3D can also be a problem, and sometimes you can install CompuCell3D, but it doesn't work. This is something I found with version 4.7. I still didn't talk to them about it, but 4.6 works fine. 4.7 I can install, but I cannot do an import CC3D in my script. For using a cluster that has Slurm as system, you can use all basic Linux syntax. So all those commands like cd to change directory, rm to remove something, or for example, um, tar, gz, everything to compress a folder, or all these Linux commands you can use in a Slurm cluster. However, there are specific commands, for example, sq-u and the name of your user to list all the processes you are running on the cluster. This is specific for the system, so Slurm has its specific commands you use to get information about your user, your simulations, etc. For using clusters, we recommend you install CompuCell3D via Conda because it's more generally accepted. Installing via binaries can be trickier. People do that. That's how people used to do it before we switched the installation to Conda. And it also reduces the likelihood that your installation interferes with other software in the cluster. Because if you install CompuCell3D via Conda, it is contained within your environment and you guarantee you have only one Conda software. This is very much recommended to use an appropriate Python IDE that has code autocompletion and variable explorer. I use Spider. You can also use PyCharm and VS Code. I use Spider because it comes with Anaconda 3. I am lazy. I'm too lazy to switch to VS Code, but the best possibly here is VS Code because VS Code also has built-in CC3D code, which I cannot access through Spider. You have to run your IDE in the environment where CompuCell3D is installed, Or, for example, if you have VS Code, you can link the kernel to the Python inside your CompuCell3D environment. That also works. So there is some setting up there if you're using one of these platforms. But this is just recommended. It's not mandatory. So this is why having a dedicated IDE is very valuable. So here in the code I'm showing, I write volume specs and dot, and it gives me a list of all the modules, all the methods that are contained within this volume specs class. So I don't need to be constantly switching screens between my code and the documentation to understand what's going on. If I just hover over one of these options, the software already shows me everything that this method does. So I know what are the inputs, what are the outputs, and everything is here. Another very good thing is it spots mistakes, like very trivial mistakes. For example, here I am declaring a class and giving steppable base pi to it, but I did not do an import of steppable base pi. And the software already spots this mistake and tells me that I need to define this steppable base pi. If you're using idle or like a basic text editor or even to edit, this is not available to you. So you have to run, you have to interpret the error in the console, and this might take time. Something that is absolutely necessary, in my opinion, to build these codes is to have the GitHub demos open in your browser. So Professor TJ Siegel, he built demos that use pure Python instead of XML to edit. And you can access these demos via this link over here. And I'll open this and also paste the link in the chat. You can see here we have adhesion demo, we have chemotaxis, sorting demo, and when I go into one of these, you can see this is all Python code. It is very well commented, so very well explained what each part does, and it has all the code you need. So if you want to know how to set your pod specifications, this is the code, so on and so forth. So I'm gonna paste this link into the chat because this is how I do things. I come here to the demos and I basically copy and paste the code, TJ's code, into my simulation, and then I just modify on top of it. So I don't memorize this. I don't know exactly the structure. I just copy and paste and modify. Okay, so that was why do we care about HPCs? Now, why do we care about deploying a simulation online? So there are a couple of reasons why you want to deploy your simulation online. The first one is when you're publishing a paper, a referee may want to run your simulation to see if it really works, right? And having to install CompuCell3D just to run your simulation. So for example, sometimes one of the referees, let's say you're publishing a model on tumor. And then one of the reviewers is a biologist specialist in tumor. He doesn't even know how to install CompuCell3D in the first place, most likely. So people come from different backgrounds, and having a quick one-click run that you can provide to your referees with very, very simple instructions, rather than, okay, first you go to this website, then you install this. If this error happens, then you have to do this. It can be a obstacle to their analysis. Shareability is key for modelers to reproduce your work in other platforms and as an exercise. So often in modeling classes, we access papers and we reproduce their work. And if they don't provide easy access to their code, it's much harder to do replication. Sorry, reproduction. It also increases the likelihood that people may use your simulation for their projects or even continue your work as their own. And this will probably give you more citations in the end, which is all you care about, I'm sure. Okay, this is a joke. Uh, People without background in modeling and computing can run your simulation very easily. So this is always something that amazes me. Sometimes I am talking to a friend and he's asking me what I do, and I explain like what my simulation does, and they are intrigued. They want to see it doing its thing, and then I can, in any computer, just open a website and run the simulation. So this can be very handy. And I can imagine this having uses in, for example, conferences. Yeah. Okay. Now let's talk about why we care about neural network surrogates. So let me start with what is a neural network surrogate. So a surrogate is a replacement. A neural network model is a deep learning model where you specify a structure of matrices and they learn from inputs trying to predict the outputs. So this is not your actual model. This is a replacement for it. But if you give it enough data, it can become quite good at predicting the outcome. So it becomes a replacement in the sense that you don't need to run your simulation anymore. You can just run the neural network surrogate instead. If you have big simulations, and in CompuCell3D, often that's the case. Let's say your simulation is a three-dimensional huge tumor. It can be computationally expensive. And one of the alternatives you have is to run many, many, many simulations. So accumulate data over the course of months and then train a neural network surrogate to make your simulation more accessible so people can do quick investigations with your simulation online very quickly because neural network surrogate runs in fractions of a second. You also can use neural network surrogates to classify your simulation when metrics are not obvious. So for example, sometimes even here in our workshop, we model system that are that get to non-trivial shapes like angiogenesis, cell sorting, and developing metrics that can classify all the possible geometrical configurations these systems achieve is definitely non-trivial. So sometimes it's even easier. Of course, building neural network surrogates is a big task, but it can be easier than developing these metrics. Um, yeah, and of course, understanding the basics of neural network surrogates can help you to integrate your simulations to neural network frameworks. Okay, so first exercise, we are going to build a pure Python CC3D simulation. This is a minimal simulation. It doesn't contain any interesting behaviors. It's not like a cell sorting simulation. It's just the minimum possible code for running your simulation and allowing you to explore and allowing you to uh, import your simulation to the pure Python framework. So the goal here is to uh, build something with CompuCell3D code that you can run in a single command like Python and then the simulation, the name of the simulation .py, and then you press enter and it's running. If you achieve this, you can do anything with CompuCell3D. You can do optimization, you can do parameter scans, the most complex imaginable parameter scans you can think of. Let me see what's the next slide here. Okay, this is part one. Set up your workspace. This is only if you have Conda installed. If you installed CompuCell via Conda, and I know some of you have, then you open Anaconda or Miniconda, depending on which Conda software you have, either from the application search menu in Windows. So let me do this example here. I have CompuCell3D installed via Anaconda, so I search for Anaconda prompt, and then here I have my Anaconda prompt, so all good. You can also open from your CompuCell3D installation folder, or just open your terminal if you are on Mac or Linux. So your terminal in Mac or Linux works as these prompt that I just opened here. So that's the first part. Then you activate your CompuCell3D Conda environment. And I didn't put in the slide the command, but it's conda activate, and then here the name of the environment. So let me do this. I have my Anaconda prompt here, and I do conda activate, and then here's the name of my CompuCell3D environment, and there we go. If you don't know what is the name of your CompuCell3D environment, you can do conda envs list. I think that's no. It's conda env list without the s. Yes. Okay, so here it's listing all the environments I have, and you can see there are many uh, different environments because I'm always installing CompuCell over and over again. So this looks quite messy. In your case, you likely have just one environment. If you installed your CompuCell3D via binaries, then if you're on Mac, you open your terminal, you navigate to your Miniconda 3 inside the CompuCell3D installation folder, and you execute this command, source bin/activate. Or you can do just bash source and then the path to the activate file from your terminal. So this is if you didn't install CompuCell3D via Conda. If you installed it with binaries, you can still activate your Conda environment because CompuCell3D automatically installs Miniconda on your machine. If you did a Windows binary install, then you navigate to Conda bin inside the Miniconda 3, inside the CompuCell3D installation folder, and you execute activate.bat. So this is something I can demonstrate here on my screen. I cannot demonstrate the Mac one because that will take some days to buy a Mac. But I can demonstrate activating Conda with binary CompuCell3D install. So to do that, I will just open CMD, command prompt. So if you type CMD in your search bar, it should just open CMD like this. And then from here, I have to navigate to the CompuCell installation folder. To do that, you can navigate from the outside, like with your file explorer. So here's my CompuCell3D installation folder, and then Miniconda 3, Conda bin. So I will copy this path, and I will do CD, right-click to paste the path, and click Enter. You can also navigate manually to that path. So now I'm inside the Conda bin, and all I have to do, and I hope this works, is to run activate.bat. And there we go. We are inside Conda now. So when you see this base here on the left, it means you have successfully activated your Conda. So from here to test if you activated the correct environment, you can do Python and then import CC3D. And if it doesn't throw an error, like mine, it just runs all fine. It means you are in your correct environment. So this is for people who installed from the binaries. Yeah. But of course, we are not going to use Python from the command line because that's not very handy to add it. So what I will do instead is open Spider. So Spider is the Python editor or the Python IDE I use to build my pure Python CC3D simulations. So you can open VS Code and you can also open idle 3. So if you don't have any Python IDE, you can just open idle, which is the same Python editor we used in the Python bootcamp 2 weeks ago. So why don't I just show you how to do that? I think it's just idle 3. Idle. Yes. So to open idle, you just type idle or idle 3, try both. And this is your idle editor. So from here you can do import CC3D to test if it's working. And basically if you can run import CC3D, you're basically done. The rest is easy. This is the hardest part. But I'm going to open Spider. Spider comes with Anaconda. I have Anaconda 3 installed. If you don't know what Anaconda is, here is Anaconda 3. It takes forever to open. Anaconda 3 is a big package with a lot of Python software. So it has code editors. It has PyTorch, I think, which is what people use to build neural network models. It has pandas, all the basic stuff. Yeah, so this is how it looks like. So it has Jupyter, it has PyCharm. Oh, you can install. Yeah, it is very interesting. But I don't want that panel now. This is my Anaconda prompt, and I know I already have Spider here installed, so I just type Spider and hit enter. This is my Python editor. So again, you can use any code editor of your preference. It doesn't really matter. So I'll probably launch the poll and see how you guys are doing. So what you have to do is this: set up your workspace, and if you have Conda install, you do this, and if you have a binary install, you do this. Okay. I feel good to proceed. So now check if your CC3D call works. So in your editor, you type import CC3D, and then you press play. If you have a Python IDE, and if you are in like a code editor, like idle, you have to run a command Python simulation.py, the name of your file, of your Python file. and press enter to run the simulation. Okay, I'll assume everybody can do this. So from here I can do import CC3D. And if I click play, all good. Nothing special. It means that I can do pure Python scripting now. So this is what I do in my free time, which is I go to TJ's GitHub demo, which I pasted in the code, in the chat. Let me do that again. So on your spare time, what do? You come here to the CompuCell3D repository and you open the demos folder. From here, you pull code. You can pull code by code, bit by bit. The requirements here, the minimum requirements is that you have your CC3D sim service import, your cell type plugin, your pot score, a volume plugin, and contact plugin, just to make sure the cell behaves, and a blob initializer. And then you get to the specifications, and yeah, there it is. It should be simple. Get the code from that demonstration. I'll give you a few minutes to pull code from that demonstration. You can also just copy and paste everything and just delete the parts that we are not gonna use. So here I have, for example, just one cell type. I don't have the visualization stuff. I just have step. This is like as crude as it can be. Oh, and I forgot that I also have to do this. I mean, yeah, I guess. Okay, so let me do this exercise too. So if you're having a hard time following, you can watch me. So here, basically, I'll do something very straightforward, which is I will copy everything and paste here. Now I'll just run to see what happens. It runs. It's not throwing an error. It's a 10,000 steps. So I'll just cancel this and at least reduce the number of steps. Again, remember, always start small. It has a performance report. Oh yeah, it has a performance report. Interesting. Okay. Yeah, we don't need these performance reports, so I'm just gonna delete the things I don't need. I don't need this. I don't need visualization. I don't need many things, but this works. Now, once you have a rough code like this, I want to show you something that TJ did not show, which is adding a steppables to your simulation. So this is something you will likely need especially because if you're running on a cluster or anywhere, you need output, and you get output from your simulation using steppables. So to do that, what do we do? Well, we come here to the GitHub demos, and we find a demo that contains steppables. So for example, let's try the chemotaxis one. Chemotaxis does not have steppables. So let's come back. Let's do adhesion demo. Adhesion demo does not have steppables. Let's do traveling cell demo. Oh, look. Here we have one class, but it's not a steppables class, so that doesn't work. Finally, here on line 70, inside the traveling cell, we have a steppable class. So I'm just gonna copy all of this. I don't need to copy these functions. And I'll paste this somewhere here in the code. And what happens? It's giving a bunch of errors. So first error here, undefined name steppable base pi, which means that we forgot to declare steppable base pi. If I come here to TJ's code, where is that declared? Right here on line 17. So I copy this, I paste here, and now we get rid of the error on line 20 on our class declaration. Okay, let me go back to the slides. So that's part 4, adding a steppables to your simulation. We copy that, and let's get rid of all that code that we don't need. So we copied a bunch of stuff we don't need. So let's get rid, for example, these location stuff, these service function stuff we don't need. You cannot have a method with nothing inside, so you have to have a pass. Then in the step function, you can get rid of basically everything. But let's say you want to print something. So just to make sure the simulation runs. So let's print like Monte Carlo step and cell volume. Get rid of this. Okay, we have our steppables, but our simulation doesn't know we have steppables unless we tell the simulation to run the steppables, right? How do we do that? We register the steppables. So there is this method called register steppable that go where? Well, CC3D sim dot, where is that? Where is CC3D sim? Right here, where we have run init start. We just add a line before the run. So CC3D, look at the autocompletion. I press tab, autocompletes. Now I type re, and it's suggesting here, register steppables. I press tab, it autocompletes. Now I give steppable equal, and then location steppable is the name of that steppable there, but we can rename to something else. So for example, I can rename this to data steppables to make it similar to the slide. And then if I give it the same name, like this, it's done. That's it. So if I run this, you see it's printing lots of things. So this is our print statement, right? It's printing 0, like the Monte Carlo step and the volume of the cell. The Monte Carlo step and the volume of the cell. Why do we have lots of zeros, lots of ones, lots of twos, lots of threes, lots of fours? Because we have lots of cells. If I build just one cell, where is that? Well, it's in the blob initializer, which is this guy here on line 78 in my code. If I just give it a radius of like 2, for example, it should, yeah, so now I have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm running just for 10 steps. So this means I have just one cell. So this is working beautifully. I'll leave the slide here, and please type in the chat if you have encountered a problem. So if you are interested in running pure Python simulations, this is the exercise you want to achieve. Okay, I'll give you a few more minutes to follow up with the exercise, and if you have problems, describe in the chat, and I'll try to help you. Okay, I think I'll move on. So congratulations. This is your first step towards CompuCell3D scripting. You know where to find code, so that GitHub link will provide you with everything you need to write CompuCell3D simulations. The steppables are exactly the same. The steppables you have in Twedit, you copy and paste them in there. Okay, there is no modification you need to do whatsoever. So that's very, very easy. The only difference is setting up the simulation and setting up the simulation loop, because we have to step the simulation manually. Which is good because we can control when we step, right? So you can write things like if something happens with your simulation, stop, pause the simulation, run something else, then come back. So it's very trivial to do things like that, which enables easier integration with other systems. Now we'll move on to cluster. Okay, so cluster here is I have a demonstration. So I will do something and you will only watch because, again, we cannot provide you with access to a cluster. And lots of talking. So first, about the file structure in a cluster. You are free to choose whatever file structure you want to work with, but it will probably look like something like this. You have a master folder with your scripts and the simulation folder with all your simulations. Usually what we do is separate each simulation in a folder. So, and the folders are ordered. So you have folder 0, folder 1, folder 2, and so on till the nth folder. And inside each one of these folders, you have the simulation file, you have the parameters file, you have a batch call, which submits the job to the cluster, and you have your output file. Of course, there is a performance impact. So the more distributed you have these things, the longer it will take, for example, to do file scans. When you are consolidating your data, you have to scan over all these simulation files, all these simulation folders. And if you have like millions of these folders, which is typical when you are doing neural network surrogates, it is often very expensive to loop over all these separate folders. But also the advantage of doing this is that the likelihood that you have like two different simulations writing on the same file and conflicts like that is minimized. But it's definitely possible to have all your simulations writing output files in the same folder. It's just not, it's a bit more risky. You have to be careful when writing your script. So if you do it like this, the script is very, very trivial. The script workflow this is general. So the code is not general, but this is. So I will focus my energies on this pseudocode here. I know that some people don't like pseudocode, and this person is here watching the lecture today, but I'm sorry, this is unfortunately the best way possible. So this is the workflow, or this is pseudocode of my script, the script that I am currently using for two projects. And the script basically do two things. The first one is creating and organizing all the folders and files. So first, it reads the files that are already there and get the maximum file, the maximum folder, the maximum name of the folder. Again, the folders are ordered from 0 to n, so I just get the maximum and then I create n more. So the next folder name is the maximum plus 1, and the last folder that you are newly creating will be max plus 1 plus the number of extra folders you're going to create. So the names of the folders, the new folders, go from max plus 1 to n plus max plus 1. Then you loop over all these folders and you copy and paste the simulation file, the parameter file, into all of these folders. This is the place where you can do parameter scanning, because whenever you're copying your parameter file, you can also modify your parameter file. So doing a copy means that you are running replicates. If you modify the parameter file inside the simulation folder, you are doing a parameter scan. And then you have all the freedom to set the rules of your parameter scan. You can do random sampling. You can do um, conditionals. For example, oh, I am scanning contact energy, but if contact energy is below 0, then set a higher lambda surface, for example. You can do all this crazy stuff to maximize efficiency of your parameter scan. And then inside each one of these folders, you create a batch file with appropriate path variables. So each of these batch files, you need a path to the simulation file, you need a path to the output file, and all of that has to be appropriately edited inside each of these batch files. Finally, you create your output file or output folder. Okay, next. So when you create all of these files, you create all your batch files. So it's a good idea to save your batch files in a list. Once you have this list, you loop over all the batch files you have and you submit the jobs. Simple as that. So you do a loop over all the batch files and you run the batch files in your script. But there is a problem. Oftentimes, clusters have maximum job submission numbers. So for example, Big Red 200 only has 500 nodes available to me, which means I can only run 500 simulations at a time. Sorry, it allows me to submit 10,000 simulations, but it only runs 500 at once, simultaneously. So I can submit like 10,000 simulations to the cluster and forget it. Just go do something else, go to sleep, and then in the morning everything is done. So we have to keep track of these max jobs number. So in the case of Big Red 200, this number is like 10,000. In your cluster, it might be different. So you have to talk to your administration or read the documentation of your cluster to know exactly what is the maximum number of jobs you can submit. So here we have a safety protocol. If the number of jobs you have running currently is less than this maximum number, you do another batch execution. Just once, just one other batch execution. If you did this batch execution, you go back and test if you are at capacity. If you are not at capacity, you run another batch job and you keep doing this loop, always checking if you're at capacity. If you are not at capacity, sorry, if you are at capacity, so if the number of jobs is greater than the max jobs, then you set like a 1 minute waiting loop. So you wait 1 minute and then you try again. And if you are at capacity, you enter the waiting loop and then you try again. And what does the batch file does? It allocates the simulation to a node in the cluster. So how to write this batch file depends on the cluster. Okay, so this is not something I can uh, help give a help that works for everybody. And finally, the simulation runs and writes results in the output file. Okay, any questions here? Okay, no questions. Let me read my notes, see what I have here. So, yes, so you can do parameter scan by changing the parameter file. You can solve replicates inside the simulation script directly instead of this macro script, which is what I usually do. And if your simulation already handles replicates, you can output directly like to the same file or write different files. And if your simulations output a time series, for example, in my case, my simulations output viral load over time. And in this case, when you are getting data from outside these folders, it is a good idea to, instead of getting the entire time series, you measure the characteristics of these curves, like the maximum inflection points, etc. Okay, that's our next topic. How do you consolidate all the data? So you'll build a script that loops over all simulation folders, access the output files, extract the parameters, and you pass that to a final average output file that contains the values of the parameters and the results. So if you have a time series, that's a little bit harder. So you may want to measure characteristic parameters of the curve, or just bring them out, do the averages between replicates, and keep them separate from each other. So I will demonstrate how I do it. So I will, for real, open the cluster and submit jobs so that you guys watch and try to have a sense of what I need to do. So I will do it in Tatooine, which is a cluster provided by Indiana University. It offers 500 nodes per user, so I can run 500 simulations simultaneously. And what I'm going to do is to perform a local sensitivity analysis. I'm not going to the details of what a local sensitivity analysis is, but it's basically a parameter scan. And on what? On my influenza A virus infection simulation that I am currently developing, and hopefully it's going to get published in a few months. Um, I will start small and I will order even less than 10. I will order like two simulations to start with. Um, yeah. And then after doing that, I will run my data consolidation script, which calculates averages and organizes all the output. This is the same, but for Big Red 200. Big Red 200 is in maintenance, so that's why I'm doing this in Tatooine. So I use specific software for accessing cluster. Putty and WinSCP for Windows, because I have Windows here, so I need these two software. If you are on Linux or Mac, you do SSH, and there are also analogous software to WinSCP for Mac and for Linux. I didn't give you um, a tip for Linux because if you are a Linux user, you don't need help. So accessing cluster depends on the specifics of the cluster. And what I'm going to show you here is only valid for my specific case. You can also subscribe to a private cluster. So for example, Google and Amazon provide cluster service, but it can be quite expensive. So ChatGPT told me it's like goes up to $2 per hour per instance. So one of the data sets I generated for neural network surrogate training would have cost between $500 and $1,000, which is not accessible for me, but depending on the relevance of your project, you have grants, you have stuff, you can definitely pay for that. Okay, so first of all, I have to access a VPN. So Cisco is the VPN I have to access. It is connected, so I'm going to disconnect, close, connect. I have to do an institutional login here. No, this is not correct. I don't know what happened there, but okay. All right, now it's correct. My password. Okay, VPN is active. Next, I open both Putty, which is this little window here, and WinSCP. Why do I use both? Because they are good for their own specific tasks. So for example, Putty I use for issuing commands and like doing like Conda activate. It's much more handy for that. And WinSCP I use for handling files, copying stuff, uh, yeah, moving files, reading files. Okay. Now I have to log in the cluster via both softwares. So in Putty here, I have already set up my cluster access. I will show you how that looks like. So I need a host name, I need a port, I need a connection type here, SSH. And in SSH, sometimes you have to check like specific protocols and stuff. This is this is going to be provided by your administration. This is specific from cluster to cluster. Mine is already set up, so I just select Tatooine here and click open, and it pops up this command. Yeah, feel free to unmute and ask me questions, by the way. This is a free-flowing session. So here, login as, okay, username, my password. Sometimes it asks for two-factor authentication. In this case, I have to open an app in my phone and go from there. Okay, so now I have my login. I'm in the cluster now. In this black window here, I'm inside the cluster already. I also do that in, okay, so caveat. Yeah, you have to configure your access, and that depends on the cluster. Now I do the same in my WinSCP. So here everything is already configured. Here you have to set the protocol, the port number, host name, username, password. And now I click login and I'm in. So this is the cluster right here in the right, and this is my computer stuff in the left. So I can move things left and right like this. So for example, if I updated my scripts here, because I added locally on my machine. So let's suppose I updated my simulation. I just drag this file here to the right and it overwrites that one. So this is very handy. If I were to do that in Putty, I would have to do SSH blah, 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 which takes forever. But here in Putty, I can do the Conda activate CC3D 4603110. And here I have activated Conda, and doing that in WinSCP is a nightmare. So I always use both. Okay, what's the next step here? Check files and check codes. So every time I enter the cluster, I check everything I have. So here I have output files. These are for real. I see that some of them are old. I have new files. Um, I have my simulation files. This is how they look like. So I have each file is the name of a parameter. See how they are ordered. So I have, for example, death probability going from 0 to 100. Sorry, 0 from 99. 100 is the total. So I have 100 replicates just for this parameter. And then I have 100 more replicates for the default parameters, so on and so forth. So this is huge, 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 huge. And imagine doing all of this locally, right? And inside each of these files, I have my simulation file, I have my parameters file. So here in the parameters list, I have all the parameters of my simulation with the appropriate value. And this is the file I added to do the parameter scan. Of course, I'm not manually editing. I am programmatically editing these files. And this is the batch file. If I double click, it will run, which I don't want. But if I come here and edit, you see how the batch file looks. It is a series of batch commands and the final blow, which is Python and the path to the simulation, which is the beautiful thing about pure Python CC3D, which is you just run your simulations by issuing this command, and all the rest does not depend on CC3D in any way. This is what you need. If you can issue simulation runs using this command, everything else in terms of script don't require to edit, don't require player, etc. You are not running in multicore? No. And the reason I don't run in multicore is because I run thousands of replicates anyways, so I just allocate one replicate per core, which is much more efficient than to do parallel programming in CompuCell3D. Do you need to save the simulation file if you already save the parameters file? I don't understand this question. Okay, so yeah. So now I have a better understanding of this file structure. I also look at my scripts. So here I open my script, and what am I looking for here? I'm looking for these macro parameters. So what is the number of replicas? What is the number of max jobs? What is the waiting time? 50 seconds of waiting time. This is my multiplier. You don't need to know what this is for, but this is my multiplier. So these are my macro parameters, the parameters I have to be careful about. So if I want to do a test run, what do? I run just two replicates, right? Just two replicates. And if I want my simulation to run extremely fast, just to check if things are working, I come to my simulation and I find somewhere is the here. So I can do something like run up to 10 steps only and stop. I'm screwing my own files now, just for the sake of the demonstration, but that's okay. So now I'm sure I have a very small simulation running and very small number of replicates. Now I can run the script. So I come to my my command, my prompt command, whatever here, and I start to navigate. So ls, I know where I am. I have to be inside this flu folder. ls here. Here you can see I have the same files and folders as in the WinSCP. So I have my script, everything. Um, so here I'll do Python. I will call the script, click enter, and the magic happens, I think. Okay, so it's submitting a bunch of jobs. Of course, I have lots of print statements to keep track of what's going on. So I know that if it's not printing this line, which is submitted batch job, I know that it's not submitting jobs, and I know where to look for. If it's not printing the correct path here with the correct parameter name, this is also hinting what is going wrong. Saving Loic. You do mean saving or copying? Because I do copy the simulation file into um, each one of those simulation folders. So here I'm going to, okay, now that I can answer. So uh, they are asking why inside the sims folder, inside these files. So in each of these files, I enter here and I have a simulation file here. Because I cannot run the same simulation twice. For each simulation file I have, I can only run once at a time because programming is sequential. And if you have two computers reading the same file, I don't know what can happen, but it's not good. So that's why I need one separate simulation file for each of these replicates. And finally, I want to check if the output is fine. So I come here in the output and I read this. And here I have all the... Oh, simultaneous reading is fine. Okay. Okay, so you don't need to do all this copying. Good. So yeah, you can try out other ways of doing things. That's fantastic. Yeah, maybe I should do that instead. So here I know I have all my output going well. I ran for only 10 steps, so I see here only 10 lines of code. This is all very, very good. So I can do a real run, right? Which I'm not going to do now, but I think you got the idea of how things work. And then I can run my average script. I think this one is for consolidating the data. So I have functions that get parameters and replicate, read output files, calculate averages, save averages. So I have all of these functions that interact with my output files and consolidate everything. Okay, so this is how it looks like. Now let's go back to the presentation. Test run, start small. Now, this is an exercise, but we don't have much time. And I will show you one more thing you can do with these pure Python simulation framework, which is increasing the shareability of your simulation. So one example is Binder. Binder is this website where you can open GitHub repositories on. So let me do that. I'll go to my navigator and I will go to my binder. And here I have, well, let me go to my GitHub where I have a proper example for this. You can also do this, by the way. The steps are quite simple.
Pedro, you can take some extra time if you need, like 15 minutes. Don't rush too much at the end here.
Okay. Okay, I will rush the demonstration and we can stop and do the steps carefully. So here I'm copying this GitHub link. I paste in Binder. I click launch, and soon enough you'll see my simulation running online. And anybody can do this. You don't need to install CompuCell3D, you don't need to install Conda, you don't need to install Jupyter Notebook, you don't need to install anything. You don't even need a GitHub account. You just need the link to the GitHub repository and a browser. That's all you need. Okay, while it's launching, I will leave the instructions here. So if you can follow the instructions, um, good question. I don't know if it works with C++. I have a feeling that it does because it supports any GitHub repository as long as it is properly set up. I think setting up is going to be different, but it should work. So the answer here is I don't know, but I have a feeling that it does. Okay, let me check. All right. So I launched my sorting demo here on Binder, and you can see that I can have more than one simulation here. So you can have a folder full of demos and simulations, and just one link to your GitHub repository, you can access all the simulations you have um, in the panel here in the left. So here I double click the sorting demo. And this is a self-sorting demonstration that I use for demonstrating CompuCell3D for um, general audiences. So I run there and it runs everything. This is the simulation running. It's not your usual visualization, CC3D visualization. We are talking about challenges visualizing CC3D simulations here. I had to write specific steppables for doing CC3D visualization. Um, I think it's here. Yes. So here I scan the entire lattice. So for X, Y, and Z in every pixel, I take the cell index, I assign colors, and I use matplotlib to plot these lattice snapshots. And finally, I have our graphs, our shared surfaces. So here people can play with it. For example, if I want the cells to sort, I can increase the contact energy between medium and one of the cells. So if this is 100 and I run, you will see um, the cells should sort. Yes. So now I have cell A outside, cell B is inside. It runs fine. And we'll see distinct graphs. So here you can see that cell B contact with medium goes to 0, cell A contact with medium goes up, and between cell A, cell A, cell B, cell B, cell A, cell B, they are more or less the same. We can try to segregate them a bit more if we do cell A, cell B equals 100. So this you can play with, you can show to your friends. Let's see what happens. Oh, yes. Okay. So now we have more segregation between the two cell types. They're trying to involve each other, and you can see the effects on the shared surfaces. So try to do this. You open the website, my binder, and you paste that link. So let me give you the link. Why not? I'm gonna give you the link to my repository. Paste the link, click launch, and there we go. It takes a while to launch, but just the first time. The other times it's faster. And finally, we have our neural network surrogate workflow, but I think I will give you guys one more minute here to accomplish this online simulation run. I am figuring out, or I will try to figure out how to do 3D visualization on Binder. I have not been able to do that. Maciek said I should ask the Binder people, the devs, to see if I need to install something. It works. Okay, so try, got it running. Yeah, usually when I have 1 to 2 hours to do CompuCell3D activity for people that don't know what CompuCell is, don't have CompuCell installed, this is what I do. So you can be at a conference, for example, presenting your work, and then you can say, well, just open this website, paste this, click launch, and that's the simulation running. There we go. And then you can have your audience playing with your simulation while you talk, and then they don't pay attention to your badly designed presentation. Only for Jupyter Notebooks files. I think so, yes. I think it's just Jupyter Notebooks. Yes. Yeah, it supports Julia, Python, and R. I think that answers the question. So I don't think C++ is supported here in Binder. You can have XML because XML is just a string. And CompuCell3D handles the parsing under the hood. So you just need a file there. That's all you need. It doesn't need to be Python code. But it will not run C, for example. It will run Python. But again, XML is not something that you execute. You don't execute XML. Right? Right, Michael? I think XML is never executed. It's just for parsing values, right?
Uh, yeah, it's mostly you are reading the XML to initialize the values, and then it won't check it
Yeah.
per step.
Yeah, so you can have a poem there. As long as you don't run the poem, it's okay. Hmm. C Jupyter Notebook in VS Code. Yes. So if you can do, but again, like, does Binder provide a compiler? So again, so the question is like, oh no, this is another question. Okay, it's okay. Visual output would not work directly. The Windows setup we do in CC3D will not show the simulation using the binder method. So just copy pasting our code is not enough. Okay, let me read this again. But the visual output would not work directly. So the built-in CC3D code for visualizing the simulations do not work on Binder, period. The Windows setup we do in CC3D will not show the simulation using the Binder method. It crashes. It's not that you can execute and it doesn't show anything. It simply crashes. It doesn't give you any error. It crashes. That's why it's so difficult to figure out a solution. So I asked Maciek and Maciek said, just send them an email and talk to them. Okay. All right. So last topic, neural network surrogate workflow. So I am currently trying to get one to work, and this is what I learned. I hope this is relevant to you. So first step in building a neural network workflow is to understand your objective. This is the philosophical part, but it determines how you will build your neural network architecture. So for example, are you doing a classification or a regression model? This depends on your objectives. Uh, what is the surrogate going to predict? Is it necessary that you need these? Is it necessary that your surrogate predicts that thing? This also depends on your objective. Then you have data acquisition, which often requires HPC for generating huge amounts of data. And in data acquisition, you worry about the quality of your data. For example, is it statistically significant? So in my case, I was trying to do this for estimating cell diffusion, and I realized that I need to run like 100 simulations to get good statistics. Otherwise, how is the neural network going to predict something that is mostly noise, right? Is the parameter space relevant? So does your data set consist mostly on like uh, simulation behaviors that you're interested in capturing? Or do you have like 90% of junk parameter sets? Is the system at steady state when you take the measurement? In other words, if you want to measure the final number of cells in your simulation, did you run it for long enough? Like, is there a process still taking place? Is your metric representative of the behavior of your simulation? So, for example, if you are doing cell migration and you measure cell speed is not a good metric for characterizing cell migration. You may want to pick, for example, diffusion or mean square displacement to characterize cell migration. And how much data is enough? Like, you are running, let's say, 10,000 simulations. Is that really enough? Is that compatible with the dimension of parameters of your simulation? Usually, no amount of data is enough for neural network training. Understand your data. This may be the hardest part. It is dependent on the system you are trying to analyze, and it depends on how you analyze it. Here you're looking for data imbalance. So data imbalance is, for example, you have a parameter that goes from 1 to 10. If your parameter is below 9, your simulation behaves like A. And if your parameter is 10, it behaves like B. So you have a 1 to 10 ratio of B behavior and to A behavior. So this can make it difficult for your neural network to predict cases where the simulation behaves like B instead of A. You are also looking for nonlinearities, outliers, noise, differentiability, chaotic behavior, all that stuff. So all of those are tricky to analyze and interpret. So this is probably the hardest part. Then you build the network architecture. I usually use PyTorch because it's the one I learned, but you can use other frameworks like Keras, TensorFlow, They all provide methods built in and classes which you can basically copy and paste and adapt to your case. You also are choosing a loss function, L1, L2 loss for regression models, and an appropriate optimizer. For example, Adam is a typical one. And this is a place where you want to play with. So you want to try different loss functions and different optimizers, see which one works best for your case. Then you have the training. Training may take time. You have to choose an appropriate learning rate and change the learning rate as the neural network system is training. So if it's learning too slow, you increase a little bit. If it's learning too fast, you will see fluctuations in the loss, and then you may decrease it. Usually what I do is I start with a small learning rate, and then I increase it bit by bit, like multiplying by 1.5 or multiplying by 2, until I reach a sweet spot where I see some fluctuation, but not too harsh, and it has a decent slope, negative slope of the loss over time. Then you are also trying to compare the normalized, it has to be normalized, loss between the training dataset and the testing dataset. We always split the dataset between training and testing to reduce, what is it called? Bias, to reduce bias in the neural network training. If your loss doesn't decrease, maybe your architecture is inappropriate. You can try, for example, increasing the number of parameters of your architecture. If the loss is too noisy, maybe your learning rate is too high. If your loss does not seem to plateau, to decrease and plateau, reach a minimum, it suggests that you should probably increase the learning rate or run for longer, which means run for more epochs. If the training loss decreases, but the testing loss does not, it suggests you probably have overfitting of the data. So it's fitting very well the training set and not fitting very well the testing set. Then to check if your neural network really understands what you're there is no understanding here, but if it can accurately predict the outputs given the inputs, you plot prediction against the real data. So you always have to do this. Just looking at the loss is not enough. So if you see that the loss plateau, but your neural network predictions still don't match the data, then it suggests you might have to change the architecture or you have a problem in your data set. You may have not acquired your data with quality. Maybe your data doesn't behave very well. And if you're handling high dimensional data, for example, 4 parameters or more, filter the data set to do the plots because it's very hard to visualize a 4-dimensional plot. Even a 3-dimensional plot, it can be very hard. So you are looking for slices. And when you do slices and plots, you can also have a sense that you have enough data on your data set to populate the slices you are taking. And if your system is high dimensional, one of the solutions for compensating for it is to decrease the range of your parameter sweep. Because if all the parameters have complex interaction in your model, then scanning big ranges on each parameter may lead to like you never have enough data because it's so high dimensional. So you may want to pick a point where you were interested in analyzing and just scanning around that point, let's say twice the parameter and half of the parameter range, more or less. And then generating as much data as possible in that small range of parameters, and then training your neural network with it. So uh, I have a I have code for neural network training and a dataset, which you can download from the student materials folder. And the data is very well behaved. I basically randomly sampled a hill function, which is a nonlinear function. So you have the neural network code there, and then you can set the architecture you want. You can play with the size of the neural network. It trains really, really fast. So that's nice. And you play with the learning rate, the number of epochs, and all the code is set up so that you can, at the end, compare the neural network prediction with the data, with the actual real data. You can also try different things, for example, introducing noise to the data to see how it affects the prediction of the neural network. Uh, Testing noise is especially good for a framework to see if your framework is not overfitting the data, because it should ignore the noise and get only the overall behavior of the data. So if it is predicting exactly every point, the likelihood of overfit is very, very high. And I guess I'm done.
Oh yes, is it possible to have multiple views? Yes, you just make two viewer windows and set them to the same output, right? And then you can rotate them to whichever views you need.
Yeah, you can have as many views as you want. If you want to make multiple screenshots, you could have a 2D section and a 3D rendering, or a 3D rendering with surfaces and without surfaces. You can do multiple ones. And those are saved. There is a screenshot descriptor file, which in principle you can modify. And in principle, when you run on a cluster, you should be able to render according to that. For details, probably need to go to Maciek, though, or the manuals. I am be upfront that I have not done that.
Is it possible to have well, how would you do a semi 3D simulation where you have layers at different Z coordinates, but they're fixed so they can't really change in Z?
So that's supposed to have been added on into CompuCell in the latest version. I haven't played with it. We'd call that a 2.5D simulation. And to do that, you have to change the updating so that the energy functionals are calculated in 3 dimensions, but the voxel updates, where you do a voxel copy, are only done in 2 dimensions. And in principle, that's possible, but I've never done it. Classically, what we would do is we would do if you're only doing 2 layers, it's possible to define the simulation so that you don't have movement between the 2 layers. And so in our simulations of the viral infection in the lung, we'd represent the top surface of the lung epithelium in 1 layer and the immune cells moving in the 2nd layer. But the current version of CompuCell in principle allows you to have as many layers as you want to do that. That would be something, if it's not fully implemented, that would be something that would be a nice extension to have. And so it's something we can talk about, but it is possible to do it. TJ also has through his sim service architecture, would allow you to run the individual simulations as separate 2-dimensional simulations and then couple them, but that's going to be quite a bit slower to run. So do you need more than 2 layers, or is 2 layers enough? That's the key question.
2 would be enough here, but they would respond. The energy would depend on the cells in the other layer, but then they wouldn't be able to copy up into those higher neighborhoods, higher layers.
That's right. That's how that's done. Typically, it's when you want to model some surface and then you want cells to be moving on top of the surface that you do that in 2 layers. So that's certainly possible.
Okay, thanks.
And if you look at the simulations that we published of immune response with viral infection, you can see how to do that.
Okay.
You have to be a little bit specific about how you pick the energies to get that to work, but it's possible.
That'd be like a C++ update.
Sorry?
That would be the custom plugin update. Do the
No,
energy, right?
no, you don't need it's for 2 layers. It's already there. We've done it with existing CompuCell.
Oh,
Now, as I believe Maciek has added actually specifically in the XML the ability to say 2.5D. And in that case, that it would pick the copy rules would be a little bit different. But I'm quite confident that he said he had implemented it. But I'm not sure how you turn it on. And all you have to do that is when you pick the lattice update neighborhood, you pick in 2D rather than in 3D. Everything else is 3D.
4.6 further has it.
Yeah. So it specifically says that 4.6 implemented it.
Found something that mentions 2.5D in the C code. That's how I found the energy scaling. So we can look. I found this call in boundary strategy, dimension type dim 2.5D.
Okay, so it's so dim
Don't
underscore
send
2.5D is what we need to look for.
So you can see supporting 2.5D